During the Second World War, a command could cross an ocean as a radio signal long before a courier could move it. That speed created a brutal bargain. The enemy could hear the transmission too. We are here to determine the GOAT of World War II electromechanical cipher machines for strategic and operational traffic. The field is World War II electromechanical cipher machines for strategic and operational traffic. A cipher machine, therefore, had to make intercepted orders useless without slowing the people who needed to send them. An electromechanical cipher machine turned ordinary text into ciphertext, meaning letters that appeared meaningless without the correct settings. Many designs used rotors, wired wheels that substituted one letter for another, then moved so the substitution changed after each key press. The moving alphabet was the central trick, and its movement was often the central weakness. The field here is narrow, machines used for strategic or operational traffic during the war, not hand ciphers, one-time pads, or purely tactical devices. The winner must combine 4 things: resistance to real enemy attack, useful operating scale, dependable service, and strategic consequence. An astronomical key count on a brochure is not enough. Cryptographers learned that security was rarely just a contest between 2 pieces of machinery. Operators reused phrases, chose convenient settings, or transmitted predictable reports. A codebreaker could use a crib, a suspected piece of plain text, to test whether a guessed setting produced meaningful text. Human routine could turn mathematical possibility into a practical attack. Operational design mattered just as much. A machine could be strong and still fail if it was too slow, too fragile, or too difficult to key correctly under pressure. Portability favored armies and ships. Automatic printing favored headquarters. The best system had to survive tired operators, bad weather, vibration, and an endless appetite for messages. Cryptanalysis, the systematic recovery of hidden text or keys, also became industrial. It combined mathematics, linguistics, captured documents, traffic patterns, and purpose-built machinery. Once a cipher revealed a repeatable structure, the attacker could build equipment to search that structure far faster than people working by hand. That makes this comparison harsher than asking which machine looked most complicated. Enigma protected enormous volumes of German traffic. Purple carried Japan's highest diplomatic messages. Lorenz served German high command. Typex protected British communications. Each solved a real wartime problem, and each forced the enemy to respond. The decisive question is what happened after the enemy committed talent, time, captured material, and machines of its own. A wartime cipher earns greatness by remaining useful after contact with a serious adversary. The field is not a museum shelf. It is an arms race conducted through intercepted signals. Enigma became the symbol of machine cryptography because it was genuinely formidable and widespread. It handled tens of thousands of German tactical messages, compact enough for field use and quick enough for routine traffic. It turned secure communication into something a trained operator could perform. A key press sent current through a plug board across a stack of rotors, through a reflector, and back by another path to light a letter. The plug board swapped letter pairs before and after the rotor maze, multiplying the possible settings. Changing rotor order, starting positions, and plugs created an intimidating daily key. Its practical strengths were substantial. Enigma needed no enormous communication center, and different networks could issue separate keys. Yet most versions advanced their rotors in a regular pattern. That regular stepping did not make the machine easy, but it gave codebreakers a structure they could exploit when procedures or messages supplied enough clues. Polish cryptanalysts first broke crucial Enigma systems before the war, and British and American teams expanded the attack with captured key material and bombs, machines that tested many rotor settings. The Allies read significant German traffic for much of the conflict. Enigma transformed warfare, but it did not keep its deepest promise. Purple faced a different task. Introduced in 1939, it protected Japan's most sensitive diplomatic traffic. Its designers replaced conventional rotors with telephone-style stepping switches and divided the alphabet into a group of 6 letters and a group of 20. For about 18 months, American cryptanalysts could read neither the messages nor the machine. Then Genevieve Grotjan found a recurring relationship in the ciphertext. The breakthrough did not produce a captured device. It revealed enough internal behavior for the team to reason backward from intercepted messages. Inder Leo Rosen then built an American analog of a machine he had never seen. Its banks of switches reproduced purple closely enough to decrypt Japanese diplomatic messages. That achievement was extraordinary. The attackers reconstructed the logic of the hidden machine from the shadows it cast in traffic. Purple yielded intelligence of enormous value, but the machine's field was narrow, and its security had already failed before the United States entered the war. Parallel transmissions in older systems, repeated diplomatic language, and readable versions of the same messages helped supply clues. Purple was strategically important precisely because the opposition could read it. Lorenz raised the stakes again. It connected to a teleprinter, an electric typewriter that transmitted typed characters and carried long messages between German high command and senior commanders. A single transmission could contain thousands of characters and expose decisions at the highest level. The Lorenz Cipher attachment used 12 wheels with irregular pin patterns. 5 wheels altered the teleprinter characters, 5 added a second changing pattern, and 2 controlled when part of the system moved. It automated traffic at a speed and complexity far beyond a portable field Enigma. Its collapse began with an operator mistake in 1941. A long message was sent twice with the same starting settings, creating what codebreakers called a depth. 2 ciphertexts produced by the same machine state. The operator shortened the second version, giving John Tiltman and Bill Tutt the foothold needed to reconstruct the unseen system. Even after the machine's logic was understood, finding the daily wheel settings remained punishing. Early procedures also transmitted a 12-letter indicator in clear form to specify starting positions. German changes improved that weakness, but Bletchley Park kept adapting. Security became a moving contest rather than a single solved puzzle. Colossus, an electronic machine built to test statistical possibilities at high speed, eventually accelerated the attack on Lorenz traffic. The result was intelligence from German high command itself. Lorenz was a remarkable communication system, but its complexity still exposed patterns, and one operational error helped open the door. Typex was Britain's harder answer to the rotor machine problem. Adopted before the war, it used 5 rotors, and changes intended to avoid weaknesses known from simpler designs. It was larger than a field Enigma, but its keyboard and printing mechanism made sustained office traffic practical. British services used Typex widely for high-grade communications. Some versions could process roughly 300 characters a minute, and the machine evolved through wartime marks. Its printers reduced transcription work, while multiple rotor sets and internal modifications complicated an attack. Typex also became part of the combined cipher machine arrangement used for secure Allied communication from November 1943. British and American equipment could exchange common traffic without exposing each nation's highest security system. That interoperability gave Typex strategic reach beyond a purely domestic machine. No wartime break comparable to those against Enigma, Purple, or Lorenz is documented in the historical record used here. Typex therefore reaches the reveal as the strongest rival, proven, scalable, and apparently secure in service. Its limitation is subtler. It strengthened the familiar rotor architecture, but did not transform the predictability of rotor movement as radically as the winner did. The GOAT is Cipher, the American rotor cipher machine jointly developed for the Army and Navy. The National Security Agency describes it as the only machine system used during the Second World War to remain completely unbroken by an enemy. It faced German and Japanese attention, not mere obscurity. That record alone is exceptional. The way it achieved it is the real reason it wins. Cipher grew from a rare collaboration across services that usually guarded their own designs. William Friedman and Frank Rowlett brought Army cryptanalytic experience. Lawrence Safford represented the Navy. Friedman had studied earlier rotor machines and shown that regular stepping could leak structure to statistical attack. The design team therefore treated predictability itself as the enemy, not merely a shortage of possible keys. Inside Cipher were 3 banks of 5 wheels. 5 cipher rotors transformed the letters. 5 control rotors generated signals, and 5 smaller index rotors decided which cipher rotors would move. The control and index banks did not merely add substitutions. They produced an irregular schedule in which different cipher rotors could move from one key press to the next, frustrating any simple mechanical rhythm. That distinction matters. Enigma's rotor motion followed a comparatively regular mechanical progression. Keba's motion only appeared random, but the pattern was so complicated that German cryptanalysts never mastered it, and Japanese teams abandoned their effort. The machine denied them the stable rhythm on which a practical rotor attack depended. The security did not remain trapped in a laboratory. Keba was motor-driven, had a full keyboard, and printed its output on a paper strip. Operators could change removable rotor arrangements and settings, while the machine handled the repetitive electrical work. It was heavy and demanded power, so it was not the machine for every foxhole. For headquarters and ships, however, it converted formidable machinery into a repeatable process. More than 5,000 machines were deployed by 1943, and well over 10,000 existed by the end of the war. The Navy used them from submarines to battleships, while the Army protected high-level networks. That was far fewer than Germany's Enigma total, because the United States used other devices for much tactical traffic. It was still enough to make Cipher a strategic system, rather than an exquisite prototype. Against Typex, the verdict is close but clear. Typex was easier to integrate into British communications, and built an impressive wartime record. Kebaba was heavier, more complex, and less suited to routine tactical distribution. Yet this field rewards the system that combined meaningful deployment with the strongest demonstrated resistance to enemy cryptanalysis. Kebaba's irregular stepping supplies the stronger technical explanation for that record, rather than leaving success to favorable circumstances alone. The two systems even met through the combined Cipher machine project. Hand equipment allowed Britain, Canada, and the United States to exchange Allied traffic from late 1943. The compromise version sacrificed some of the original design's security for interoperability, which reveals the cost of the full machine's protection. Allied compatibility had to be engineered around it. No Cipher machine can defeat capture, careless key handling, or unlimited future computing power. Declassified history records a near miss in the China-Burma-India theater, where physical security around the system became the danger. Modern researchers have also attacked SIGIBA with consumer computers, under assumptions and computational resources unavailable to wartime enemies. That does not erase the historical result, it defines it honestly. Its GOAT claim belongs to the contest it was built to fight, not to eternity. In that actual contest, SIGIBA did what the others could not do simultaneously. It carried important traffic at meaningful scale, endured wartime handling, and denied determined enemies a usable cryptanalytic break. Its lesson is not that more rotors automatically create safety. The decisive achievement was breaking the attacker's expectation of regular movement. That made secrecy an engineered behavior, not a boast about key counts. That is why SIGIBA is the GOAT of World War II's high-grade Cipher machines.